So we're going to do a problem today using the work energy method. And this is one that involves a few things that are kind of different. For one, the example problem we covered last time didn't have anything to do with friction, and so I'm adding a friction component in for this particular problem. It also involves a body that is both translating and rotating, and the translation that it undergoes is not linear. All right, so these are some interesting things. What else here? It has a spring built into it. It has gravity that we've got to take into account, and so it's got a lot of different pieces that show some of the breadth and depth of what we can do with this method. So we'll start by sort of describing the problem. We have this half disc. We're given how much that half disc weighs over there, 130 pounds. It's going to roll on the surface underneath it such that it doesn't slip on that surface. Okay. As it does this, it will pull on a rope that is attached to a little brake assembly. That little brake assembly is more or less two different surfaces that are being pushed apart by a spring. Okay, so as that spring pushes it apart, it causes there to be force felt in the two surfaces there. All right. So the spring inside of the brake assembly has a spring constant of 30 pounds per inch, and before we even get started, as in when the brake assembly is in its starting position, it already has 15 pounds of force in the spring. In other words, it starts out not at the spring being relaxed, it starts out such that the spring has some tension in it, or some compression, I should say. The coefficient of friction between the matings, the kind of the friction surfaces, which that would be basically up here on the top and down here on the bottom, the coefficient of kinetic friction there is 0.4. All right, we're going to start out such that the position of the disk is described with a theta angle of 10 degrees, and at that starting moment, we also will already have an angular velocity of 200 degrees per second. Okay? And what we want to do is find two things. First of all, I want us to find what is the velocity of the brake assembly when this thing has rolled down such that the angle theta is 90 degrees. Okay, so you can kind of imagine that theta is always going to be measured relative to vertical. It'll be that face of the half disc relative to vertical. And so when that reaches down to 90 degrees, what is the velocity of the brake assembly? And then for the second part, ultimately how far does the brake assembly move until this thing essentially runs out of energy, right? So it's got some energy built into it. How far can we get that brake assembly to move before the half disc stops, basically? Once it stops, assuming that's past 90 degrees, which I hope it is, or else part B doesn't make sense. If it goes past that point, then the presumption would be that it would probably roll back and the rope would go slack after that point. But we're just going to try to figure out how far it makes that brake assembly move to the left. Okay. Do notice one thing. We have some inclined surfaces, basically, that will force this little brake assembly to compress further and further as it moves to the left. Notice those two angles of 3 degrees. Those are basically causing the surfaces to narrow, and that's going to end up putting more compressive force in the spring as everything moves. All right. One thing that I'm going to do right at the very beginning is I am going to say that I'm going to use a small angle approximation for the brake assembly. Okay, and I'm not really probably going to start with that, but I want to go ahead and say that up front, that I'm planning on using this small angle approximation. Basically what I mean by that is that if you actually do the dynamic analysis of the brake assembly, the forces that act on those friction surfaces are not, you can't necessarily say that they are going to be a normal force that is normal to the direction of the rope pull and then a frictional force that is parallel, because we have that slight angle right there. Now, having said that, if you use a small angle approximation, it basically allows you to ignore that fact, and you treat those friction forces there as if they were parallel with the direction of the rope pull. So we'll get to that in just a few minutes. All right, the big picture on this is that we have several things that are storing energy. Okay? Energy can be stored in the form of kinetic energy. It can be stored in the form of elastic energy in a spring. It can be stored in the form of a height difference, so gravitational energy. And so we need to start coming up with expressions that tell us these different energy terms, amount of energy that we've got stored, and we need to do those as functions of theta and omega. Okay, because as this thing begins to move, theta will change, omega will change, and so in order to develop this thing, we're going to need to do that. If we're dealing with anything that is a rotational body with kinetic energy, there's probably something that we should do first, right? What do you think that might be? Okay, we're going to need a parameter that isn't easy for us to just, sort of come up with necessarily. So let me actually look at this little half disc. I'll just show it kind of straight up like this for right now. The parameter that I'm talking about is the moment of inertia. Okay? Now here's the thing. We need the moment of inertia for this half disc, and we actually need the moment of inertia about the center of gravity. Here's the reason for that. We have two choices if we are going to evaluate rotational kinetic energy. Okay? One of the ways is, and I should say this, I'm specifically talking about a rigid body where the center of gravity has a velocity. That's what we have here, right? The center of gravity has a velocity. Earlier in the course, we looked at a situation where I found a moment of inertia for a body. Instead of around the center, I found it around some other location, right? That was using a principle that you can take an instantaneous center. If you find the moment of inertia around that point, then you can treat it as if it's a purely rotating body, in which case you just have 1/2 of the moment of inertia around that axis times omega squared. This problem makes that, while maybe not impossible, it makes it impractical to do it this way. The reason why is that the point of contact on this half disc is constantly moving, right? So the location of the point of contact, and the point of contact at any point is going to be the instantaneous center of rotation. It's moving, right? And it's going to be in a different location on the disc as the thing moves. So what that leaves us with is probably we want to steer away from doing it that way, and we want to steer into doing it with this expression that basically gives us kinetic energy for a rotating body is going to be equal to basically a rotational component, such that we need to find that moment of inertia around the center of gravity times that omega squared. And then to this, we are going to add a linear component also of kinetic energy, okay? Where that v squared is the velocity, again, of the center of gravity. And this problem makes it to where we're probably going to be best off using this expression of overall kinetic energy for that body. And the reason I say all that is that you know, we are going to need to find that moment of inertia about the center of gravity of this half disk. Okay? All right, so we flip back to our handy dandy table in the back of the book. As a matter of fact, I believe I have a picture of that right here. Where's our half disk? We don't have a half disk. Okay? Is there any way we could maybe look at this table and sort of mentally come up with something that would be equivalent to a half disk? Okay? So let me suggest something. Look at that thin circular disk, right? We have an expression there for the moment of inertia about the z-axis, okay? That's this right here. That's the z-axis. We have this expression for the moment of inertia around that z-axis, 1/2 mr squared, okay? So let me ask you this. If that thing was flexible enough to where I could fold it, let's say, around the x-axis and basically make a quesadilla out of it, right? Fold it around that x-axis. All of my mass that I've got, I have the same amount of mass, right? If I was able to fold it like that, I've got the same amount of mass. What else? All of my mass is still at the same radius that it was when it was like this, right? And remember, those are the two parameters that we think about when we're looking at moment of inertia. How much mass do we have, and where is that mass located radially away from the center of rotation, right? So if I take that disk and I, again, make a taco or a quesadilla out of it, right, fold it over, then it actually gives me the exact same formula, 1/2 mr squared, okay? Because there's no difference between the mass, and there's no difference between how far the mass is away from the center of gravity, okay? So what that tells me is that for this, if I want the moment of inertia about the point C right here, I can do that. It's just 1/2 mr squared. But that's not what I want, is it? Okay? What do I want? Okay, this is maybe IC. If I want it about the center of gravity, I got to do something to get it around the center of gravity, okay? And so this is where the parallel axis theorem comes in and is really, really nice, okay? We know that the center of gravity of this thing is going to be equal to 4r over 3 pi away from that location, okay? Now, the parallel axis theorem, you might remember, is used, where you basically are finding a moment of inertia for some other axis not through the center of gravity. You do that by finding what it is through the center of gravity and adding mass times radius squared, or mass times the distance squared between those two axes. So we have a little bit different situation because we are starting out with an axis that is not at the center of gravity, and we want to move to the center of gravity. What do you think we should do? Subtract it, right? Because that's how you would go the opposite direction. And that only works as long as you're going from some other location to the center of gravity, which is what we're doing, so that's good. So 1/2 mr squared, okay, minus, and then here we're going to have the mass of the thing again, times 4r over 3 pi squared. All right, so what I'm going to do is go ahead and hop over to Mathcad, and I'm going to go ahead and get this expression built into my Mathcad sheet. All right, here's Mathcad. You'll notice here I went ahead and started by showing the problem and putting in a bunch of parameters that are going to be useful for me in this problem. Let me start down here by actually, because this is a parameter I'm going to need to use a few times, let me start by defining a distance from point C to my center of gravity. And maybe I'll just name it r sub CG. Okay, it's going to be equal to 4 times, let me explain some of my variable names up here, mass of the half disk, that's why I used HD right here. It's 130 pounds in Mathcad. If you just put LB like this, that is a mass, and you don't have to mess with it any further than that. Mass of HB, that's basically half of the brake assembly. So 10 pounds per half is what that is right there. Anyway, R sub HD is the radius of the half disk. Okay, so that's what I want to use right here is R sub HD. Okay, and then all of this is going to be divided by 3 times pi. Okay, and if you want to see what that is, I like to do this as I go along with Mathcad a lot of times, is just make sure that I'm not, I'm going to do that in feet, not far off with what I'm thinking. Does it make sense that that should be about 1.698 feet away from point C? Seems close enough to me, okay? All right, and put a border on that. All right, so now what? Now I'm going to figure out what my moment of inertia is about my center of gravity. Okay, for that I'm going to do 1/2 of the mass of my half disk. And it's really nice working in Mathcad because you don't have to mess with the units. I don't have to go to slugs. It's already built in there that that is a particular mass, because that's how I defined it up there at the beginning. Okay, so I have that. This gets multiplied now by what? Okay, R squared, right? So I do again R sub HD squared. So that much of what I have so far is the moment of inertia about point C. From that I need to subtract the mass of the half disk, all right, multiplied by the radius of the half disk. Let's see, not the radius of the half disk. I need here the distance between point C and the center of gravity, which is that R sub CG that I just found. So R sub CG squared. Okay. And that comes out in a certain number of, there it's saying meters, kilograms, meters squared kilograms. I'd probably like to see this instead in like slug feet squared. Okay. All right. So far, so good. We now have this parameter that is at least somewhat helpful to us. All right. Where do you want to go next? I'll let you help me drive. All right. What do you want to do next on this problem? Someone suggests a free body diagram. Well, how about this? Let's do, I already put this problem or this equation up here, right? This 1/2 Ig omega squared and 1/2 mvg squared. Why don't we work with that, okay? And come up with a function that gives us how much kinetic energy we've got in the half disk, all right? So to do that, let me actually redraw my half disk again. And I'm going to draw it such that it's now at some angle. Okay. So it's at an angle of theta. Okay. Now here's what's tricky, all right? We also have an omega moving like this. Okay, we have a couple other things. I'm going to move that down here a little bit. Can I relate omega to VC? Okay, so that's good. We actually know here that VC is equal to omega times the radius of this body, which was going to be 4 feet, or the variable that I was using in Mathcad was r sub hd, right, for half disk. So I'll go ahead and put that up there. That allows me to make at least one relationship, okay? But that's actually not the velocity I need to evaluate my kinetic energy. I need a velocity of a different point. I need the velocity of the center of gravity, and I'll just show that right here for right now. Okay. That distance right there is my 4r over 3 pi. Okay. And then I have a point down here directly below my center point, and that is, I can call it an instantaneous center. I know that because it is rolling without slip on a surface that has 0 velocity. All right, so that's the instantaneous center. And since I know that's the instantaneous center, I can draw a line that goes from here up to here, and that allows me to say what direction the velocity goes of this point right here. It's going to be perpendicular to that line. Okay, so this is the velocity of the CG, or I called it up there VG, right? Okay. Well, that's kind of weird, though. Why? Well, it's weird because how am I going to figure out what that VG is relative to omega? Because one of my problems here, and I should have probably painted this picture a little more clearly, my problem here is that omega is related to VG. They're not two different things. Like, in other words, once I know omega, I should be able to find VG, but I need to establish a function that actually lets me do that.
Can you say that VG is equal to VC plus?
Okay. One of the ways you can do it, I think the recommendation here is if you know what the velocity is at C, you can figure out what the velocity is at G with our relative velocity equation, right? VC plus omega R, omega cross R, right? That's one of the ways we can do it. I actually think that there is an easier way to make this happen, and it's with this instantaneous center method, okay? And what it involves is basically finding this length right here as a function of theta. Okay? So let's think about how we would do that. All right? We know this length right here, don't we? What's that length? That's just r sub hd, yeah, 4 feet for this problem. Okay, we also know that side over there. We also know something else. We happen to know that this is theta. So that means what for over here? That angle right there is going to be 90 degrees minus theta. And where do you think I'm going with this? Okay, where I'm going with this is this. If I'm trying to figure out the length of this side over here, okay, I don't have a good name for it, but let's just say, I'll just call it L, okay. If I'm trying to figure that length over there, I can use law of cosines. All right? Yeah.
So the reason that you're using the law of cosines is because that instantaneous center is going to change.
Yep.
So you're setting up
A function in terms of theta right? So this is actually, that's a really good, astute point. He says, I'm doing this so I can set it up as a function of theta. So I actually could say this is going to be a length as a function of theta. Okay? And the way that works is that I will have r sub hd squared plus 4rhd over 3 pi squared minus 2 r sub hd 4r sub hd over 3 pi cosine of 90 degrees minus theta. All right. Well, once I know L, how does VG relate to omega? Okay. Yeah, omega times this L of theta, right? That I just established. So let me go ahead and get that put in to my sheet as a function. Okay, so I'm going to go back to my Mathcad sheet, and this is basically what we had. We have here, and I'll tell you what, I'm going to do it all in one shot just to save a little bit of time, right? VG is omega times L of theta. So what I'm going to do is I'm going to say V G, all right? And it's going to be a function of both omega and theta. Okay? And it's basically just going to be equal to omega times the square root of, here I've got r sub hd squared, plus, all right, for this other one, I may as well call that r sub cg squared, okay, minus 2 times r sub hd times r sub cg times the cosine of 90 degrees minus theta. Okay. And a lot of times what I'll do is after I put one of these in here like this, I like to put in a test case and see if the values that I'm getting make any sense at all. So VG, okay, let's just put in my initial, remember we start out with an initial omega. Okay, so I'll plug that into this function, and then let me also plug in my initial theta as well. Okay, so what I'm doing here is evaluating right at this instant in time. This is the velocity associated with the center of gravity of this body. Okay. All right. So that's kind of interesting. All right. But what's powerful here is that this is now a function that I can just call, and it gives me, relative to omega and theta, it gives me what this velocity is of the CG. All right. So why don't we go ahead and put in another function that is basically my kinetic energy of the half disk as a function of the omega that I'm dealing with there, and then because of how this geometry is changing, it is also a function of theta. Okay, so that's what I'll do here. Let me do it as a delta E. I'll put delta E with a K next to it for kinetic, and then I'll put a subscript of HD for my half disk. Okay, and put in an omega and a theta. Okay. So this change in kinetic energy is going to be equal to 1/2 times, I just figured out my I about my CG, right? So I multiply by that. Then I multiply by, okay. The omega that I'm putting here is a general omega, meaning you move to some location and it's going to have this, velocity to it. The change in energy is basically that relative to what it started out with. And if you want to do that, you basically have to take the difference of the squares of those two angular velocities. So what we'll start out with here is omega squared, okay? But then we'll subtract whatever the initial omega was squared. Okay, and this will give us the change in the amount of kinetic energy to our new location relative to how we started. Because remember, we're starting here with an initial angular velocity of 200 degrees per second. All right, that handles the angular portion of the kinetic energy. All right, but I also have a linear portion of kinetic energy that I've got to deal with. So I'm going to add 1/2 times the mass of the half disk, okay, times, and this works very similarly, right? I can put in here Vg, okay, V sub g of omega and theta. Okay, that is all going to be squared, and I will subtract whatever my initial linear velocity was of the disk. So I subtract Vg. Okay, now this, I'm just going to take those initial values, right? My omega sub I and my theta sub I. Okay, and what that functionally does is it plugs those initial values into that function and puts it in that spot right there. All right, now I can check that out if I want to. I can plug in, this is one way to kind of find mistakes. If I plug in, let's say this value right here with omega I and theta I, what should I get? Okay, good job. He says 0. Why?
Because you're subtracting the same values.
Right, it hasn't gone anywhere. This is the amount of energy that I have right at the beginning, so the amount of change from that point to that point is not going to be anything, right? So it's good that that turns out to be 0. If it didn't, I'd be worried about my function that I put in there. All right, so far so good. So now I've got a function that gives me kinetic energy for the half disk as a function of omega and theta, okay? Do I have any other kind of kinetic energy that I might want to consider? Okay. Is my brake assembly massless? It is not, okay? Its velocity, the velocity of the brake assembly, is related to the velocity of the half disk, right? So I should be able to come up with something in terms of similar variables there. I should be able to come up with something that gives me my change in energy, my change in kinetic energy of the brake. So I'll just call that Ek sub B. Okay. Now, what is it going to be a function of? Okay, go back to we said a second ago, Vc is just omega times r sub hd. Well, Vc is the same velocity as is going to be transmitted through the rope to the brake, right? All that just translates linearly, Okay, so I'm just going to go ahead and say here that that is going to be a function purely of omega. Okay, the formula for that is 1/2 times, okay, I need to now take the mass of the brake assembly. All right, what does it say in the problem? You got a question?
No, I didn't mean to interrupt.
That's all right.
Okay, so because of the fact that you're only using omega, like the reason you can say you're only using omega is because that C is technically a disk, and so in C's eyes it's only translated.
Okay, so the question is, why is it that I only need omega? The biggest high-level answer is it's because the velocity that's transmitted to the brake assembly is not also a function of theta. Okay, and the reason for that, you were right, is because it is attached to the center of rotation. And so how much velocity point C has is purely a function of omega, not also of theta. So that's why that's the only thing we need there. All right, keep in mind we have half of the brake assembly weighs 10 pounds, and each half weighs 10 pounds. Okay, so how much does the whole brake assembly weigh, assuming the spring is massless? Let's say the spring, we're not going to count that. Or maybe it's included in that estimation. It'll be 2 times the mass of half of the brake. Okay, then what? All right, well, for the next part, we need to have the difference in the squares of the velocity of the part for the 2 different locations. So we'll start with what it ends up with, right, and subtract what it started out with. Okay, so here we do VC, but VC, I don't think I made a separate function for that. Let's just punch it in here directly. So all I need to do is do omega times R sub HD, according to what I put on my written sheet. All right, so I have that squared. All right, minus, and here I'm going to put what I had initially, squared, okay, which would be omega sub I times R sub HD. And then all of that is going to be squared. All right. So now I've got my kinetic energies taken care of at some random some random position or omega value that I've got here. All right, what other ways am I storing energy here? How about gravity? Is gravity a thing? Let me ask this. Is the center of gravity of any of my moving parts here changing height as a result of the thing moving? Okay.
Your center of gravity of the half disk is changing.
That's right. The center of gravity of the half disk changes as the thing rolls, right? So that center of gravity, starts out here, or, if it's up higher, and as it rolls downward, okay? So let's figure out that change in energy due to the change in position of the CG of the half disk. All right. In broad terms, we're basically talking an mg delta H, right? So let's go back over here and try to, maybe I'll do another sketch of this half disk. Okay. And keep in mind, this thing's rolling along a surface down here. All right. Now, this thing, how far it is below this level right here is based on this radius value, which is 4RHD over 3 pi times what? Does it relate with this theta right here? Yeah, it does, because what we're trying to figure out is whether it's in this position or whether it rolls a little bit further. You know, let's say it rolls down to another position here, like this, right? So now it's down like this. You're always going to be a height difference here that is going to be equal to 4r over 3 pi times the sine of theta. Do you agree with that? That's this distance right here. 4rhd over 3 pi times the sine of theta, whatever that theta happens to be. Okay, so that as that thing rolls, that can give us our height in terms of theta relative to that, you know, relative to this position or this height. Okay, all we need is a delta, so all we got to do is subtract those two, right? We could subtract two different positions that we might have given by that formula. Okay, so we'll put that in up here. We'll say my delta E, we'll call it delta EG for gravity, right? And this is for the half disk as well. This is going to be a function of what? Theta. Okay, and it's going to be equal to the mass of the half disk times G. G is built into Mathcad, so I don't have to mess with that. Times, here's my height difference. Okay. So I can take maybe my final minus my initial. So I have r sub cg times the sine of theta. Okay, minus r sub cg times the sine of, what do you think? Theta I. All right. Now, one thing I should do here is, this one's actually pretty easy to check to see if we are getting it right in terms of sines. Okay. I can take all of this and punch in let's say theta f. What was theta f? I had it defined up there earlier. I used that as my, you know, one of the things I'm supposed to evaluate is when it comes down to where theta is 90 degrees, right? Then I should have some velocity at that point, right? I've also had a change in the amount of gravitational energy. So now my question is, should that be positive or negative? And it says joules right now. I'd rather have this in foot-pounds. Not that it matters. Should that be positive or negative? Okay. Why do you say negative? That's right. The CG has dropped as a result of this thing rolling, right? So it should be negative. And I guess, you know, we could have done this a little bit more rigorously, and we would have seen that, you know, in how we set up that sum. But the other way to do it is just do an intuitive check on it and see if you have it right. Okay? It's actually due to the fact that this sine theta term is dropping it, not raising it. Right? Those values are actually dropping that level lower and lower, not raising it. Right? And I didn't even try to take that into account, but I could have negated both terms there because it was dropping and, you know, done it that way. So come up with the same result. All right, so there's a function that gives me how much my gravitational energy has changed as a result of moving through some, you know, rotation theta. All right, do I have energy going anywhere else? Okay, I do have energy going into friction. That is one of my trickiest ones that I've got to think about. So I have to do something here. I have to figure out just how much is going to friction. If I need to do that, I need to come up with a function that tells me force as a function of position. Because you might remember there is a formula that says basically work is equal to an integral from one location to another location of the force as a function of x dx. So if I can come up with a function for F, then I can figure out work. Well, what am I really talking about there? Well, here's what I'm talking about. That little block, that little break, right? It has these frictional forces that push like this, and it's based on how much compressive force we have here. Okay? Now, I decided also I'm going to make another simplifying assumption. Let me kind of justify it for you. All right? If the brake assembly itself has weight, right, then what that will tend to do is to shift there to be more load right here relative to up here. Would you agree with that? There's going to be more load down at the bottom versus up at the top. The thing is, though, as long as you continue to have force on the bottom and on the top, right, then that's basically all that does is it shifts load from one side to the other, and all we care about is the sum of the two. Right? So a simplifying assumption I'm going to do here is I'm going to neglect the weight of the, as far as coming up with these values, I'm going to neglect the weight of those pieces. One of these days, maybe I'll come back and do an evaluation not making these simplifying assumptions, the ones like the small angle approximation and this one that I'm talking about here, and show you how much difference there might be between them. But this is I'll assert to you that this is a valid assumption to make here. All right? In which case, I need to come up with how much force am I going to have as a function of x. Well, how do I know how much force I have for these, let's say this is Fn. That's the force I'm talking about, Fn. How do I know what my force Fn is as a function of x? Okay. Well, I know what it is when x is 0, right? It says here, it starts out carrying 15 pounds of compressive force in the spring. Okay? So, that's what I'll start off with, is I'll say, actually, I tell you what we'll start with. We'll start with, what does that mean in terms of deflection of the spring? In other words, what's this initial deflection, delta I? All right? Well, it's going to be 15 pounds over the spring constant, 30 pounds per inch. Okay? And what this tells me is that there's a ½ inch of sort of deflection of the spring already right at the very beginning of the problem. Okay? So why don't I go ahead and get that implemented into Mathcad here real quick. So delta sub I is going to be equal to, let's see, I think I called it F sub I, but I needed, yeah, that's what it was, F sub I over my spring constant K. All right. So far, so good. Now, how does my deflection delta I change as I move through X? Okay. Well, let's look back up here. There's this angle of 3 degrees, right? So what I would submit to you is that if I'm looking at a little triangle here, and I move through a distance of x, I'm looking at just one side right now, move through a distance of x going this way, and I start with some height right here, and this is 3 degrees, how does x relate to h? Not quite. So this is, since this is my right angle right here, right? Basically, tangent of 3 degrees is h over x, right? Which tells me h is going to be equal to x tangent of 3 degrees. Okay? In other words, for each unit of horizontal length, that's how much my height changes. But it does that on both sides, right? So I have another one that would be down here that would be doing the same thing as they compress the spring. Okay? So what I would submit to you is that my delta as a function of x is going to be equal to 2 times x tangent of 3 degrees plus 0.5 inch. And this, I meant to say this as a function of x. All right. Well, that's kind of interesting. What does that mean now for Fn? All right. All I got to do is take my delta now and multiply it by my spring constant. 30 pounds per inch times delta as a function of x. All right? Do you agree with that? Okay. So now what if these are maybe F sub F for like a frictional force? How much frictional force do I have total? That's also going to be as a function of x. Well, it's just going to be equal to my kinetic coefficient of friction times my normal force. And here's where something is a little bit tricky. There's 2 of them. All right? There's going to be that reaction on the lower side and that reaction on the upper side, right? And so I would need to multiply this by 2. Okay? And so this is the amount of resistive force that happens as a function of x as this thing moves along. Let me go ahead and implement those 3 functions in my Mathcad sheet. Okay. All right. So first of all, delta as a function of x is going to be equal to 0.5 inches, or I called that delta I. Okay, plus 2 times x times the tangent of 3 degrees. If you'll remember up here at the top, I called that phi, just to make it a variable rather than just a typed in number. All right. All right. So there's that. That's my function for delta as a function of x. Now what? Okay, I'll tell you what, I'll skip ahead one step and just go straight to my friction function as a function of x. Okay? For this, it's going to be equal to 2 times 2 because I've got both the upper and the lower, times, if I have k times delta of x, all right, that gives me my normal force, right? And then what else do I need to multiply by? Okay, what did I call my kinetic coefficient of friction? It's right up here, mu sub k. Okay, so I put in mu sub k. All right. So far so good there. There's a couple things I can now do. One of them was someone said we should evaluate friction. We should evaluate the work done by friction, right? Friction is a non-conservative force, right? It's something that actually gives up energy as we go. All right? So, maybe I'll call that W sub F, right? I'll do that as a function of x. And the function for that is the integral. In our case, we're starting out with a 0x. So we start at 0. And we go to some arbitrary value of x. Here, I'm going to put in f sub f of x dx. All right. Now, there is a question we have to kind of think about right here. We have to think about our sign of this. So we need to think to ourselves, are we adding energy or pulling energy out of the system with this? And if you decide, it's pretty obvious, we're pulling energy out of the system with this. Friction always removes energy. It destroys energy, basically, at least usefully, right? Useful energy it destroys. All right. You can decide to put a negative sign either right here and indicate this as a negative energy value, or you can do it in your ultimate energy balance that you're going to do later. I actually prefer to do it right here and say this is going to be a negative amount of energy, as in it is leaving the system. All right, so there's my work term. What else do I have? Is there anything else that's storing energy? So the half disk has got a rolling action, right? It's rolling without slip on the base. And because there's no slip, even if there's force right there, there's no movement, and so there's no energy spent as it rolls. So it's lossless. It's a lossless move as it rolls downward. Right. If it slipped, then it wouldn't be lossless. But as long as it doesn't slip, it'll roll down and it won't lose energy. Okay. All right. There is one other thing we've got that is storing energy. What can you tell me it might be? The spring. We've got elastic energy going on here. But the good news is I already have a function that gives me how much the spring compresses as a function of x, right? So doing a delta for the amount of energy in the spring is not all that difficult. Okay. Elastic energy in the spring. Maybe I'll name it like that. All right. It's going to be a function purely of x. The formula for that is 1/2 of k times the difference in the squares of how much it has compressed, right? And so what we do there is we put in delta as a function of x squared. Whoops. Excuse me. I think I'm going to have to retype that. All right. Times this delta as a function of x. That will be squared. And then we will subtract delta I squared. Okay. All right. Is any more energy going anywhere else? Probably not. I think we've got it we've got it whipped. All right, so let me put in here omega f, because what I'm trying to do is figure out what is this angular velocity of the disk, the half disk, when it gets to 90 degrees theta, right? Okay, and so I'm going to define this as an initial guess of just 1 radian per second. And if you've seen me do Mathcad sheets before, I usually make some sort of an indication to myself that that is an initial guess. I use a particular color to help me with that. Then I type the word given. Now, because I've got all these functions defined, makes it super easy, right? I just have the changes in each one of the types of energy, and I add them up, okay? So first, the kinetic energy. For my half disk, what should I put in here? Okay, this should probably be omega f and theta f, right? Because I need to actually take that at a particular location of movement, right? I'm picking off this theta equal 90 degrees. That was my theta f. I'm also solving for this omega f. So I'm going to put those in as my arguments for that function. Okay, then what? I add to that my kinetic energy of the break. Right, again, I want to make this omega f. To this, I'm going to add my difference in gravitational energy. Okay, again, for theta being theta f. And I have a change in the amount of energy in the spring. Okay, now this one's a little different. X right now is a variable, right? But X is actually related to theta. How so? Okay, think of how this thing moves, right? If you have a difference in theta, you take that difference in theta and multiply it by the radius of that half disk, that's how far point C moves, right? Because you're using theta in radians, right? As theta moves, that's how far it will make that, that center point move. And so what I'll do here is rather than put X in here, I'll do a little calculation just right on the spot that turns a theta value into an X value. And here's how that works. Okay. What we'll do is we'll put in a theta f, okay, minus a theta I, and we'll take all that and multiply it by r of the half disk. Okay, so those are all my changes in the amount of energy stored. What should I set that equal to? The work, right? So that's the amount of work. That's kind of our basic equation, is you evaluate the differences in all of your energy storage elements, and that's going to be set equal to the amount of total change in your system, right? Which is just going to be this. Now that is also a function of x, so what should I do there? Okay, I should probably hand it an argument in a similar way that I did before with that other one. All right, then what? Okay, now I'm going to find my omega f. All right. And when you get that little green squiggle like that, it's a good feeling. Okay. I'm going to change that to degrees per second. 145.326 degrees per second. How fast was it when I started? 200. So we've slowed down a little bit as we've moved down to 90 degrees. Here's one of the things that I like to do. Actually, I tell you what, we'll go ahead and answer the original question. This was not the original question, actually, right? The original question was, when you hit 90 degrees, what's the velocity of the brake assembly? Fortunately, that's not hard to get. Okay. What is that velocity? Okay. Yeah, maybe the final velocity for the brake is going to be equal to omega F times R HD. There's nothing magical about these letters that I'm choosing here. I'm just, trying to make things that make sense to me. Feet per second. Oops. All right, so that's the answer to the first question. What I was about to do a second ago is I like to go through and evaluate and say, now that I know what my final omega is, I can say where all my energy went, right? And all I got to do is go back up here and take each of these values, like for instance this one right here, and copy it down here, right? Change this to omega F and theta F, and what can I do? Oh, that's not actually the one. Sorry. That one's interesting too, maybe. What is that one? Okay, that's how fast the center of gravity is moving in a linear sense, right, at that location. So that's maybe of interest to you. That's not really the one I was trying to pick off, though. I was trying to say, what's the amount of change in my different energies? Okay, so in this case, the change in the kinetic energy for this thing, I put in my final values of these things. Okay, it turns out to be a negative value. Does that make sense? So in other words, from our starting point to this point, does it make sense that I should have a negative change in kinetic energy for my half disk? Yeah, it's slowing down, right? So there's less kinetic energy as it moves, all right? We can do this for all of the different, like we can do it for gravity, or we can do it for the brake, all right? Here I'd put in sub F and hit equals. All right, so what does that tell us? Okay, it has also lost kinetic energy because it's slowing down. The brake unit with the spring in it is slowing down. And so it's losing that much energy. Okay, I'll go ahead and get all of them in here because I think it's nice to be able to see them all. All right, the next one was my gravitational one, although I think I already evaluated that one, right? Because this one didn't matter what your omega value was. So I could do that one right from the beginning. All right. Does it make sense that that is losing energy? Okay. The CG went from a higher location to a lower location. There's a negative change then in the amount of energy associated with gravity. Okay. Another one that's interesting is the spring, right? Okay, so for that one, instead of putting x here, we put in that same, I'll tell you what, I'll just copy it from above. I put in this guy. Okay, and this one turns out to be positive. Okay, do we like that? So when you start off, the spring is less compressed. And as you move, what happens to the spring? It's being compressed, right? And so it is gaining energy stored inside of it as it moves along. So it makes sense that that would be a positive number. And then we look at, I think the last one we had there was work, right? So put in this one in here like this. And so that's how much energy we're losing as a result of the brake providing that friction as it moved. All right, so we've done part A, along with some bonus stuff. Yes, sir?
I'm still confused on how you related the delta E sub S to arc length, because I mean that's basically.
Okay, what I'm doing is I'm putting in an argument here that is equivalent to x, right? That's the argument for delta E ES right there. What I put in there is equivalent to x, so that's probably worthwhile going back and showing here that as this body rolls, right, you would know what to do if this was a full circle, right? It wouldn't be confusing to you that if this thing moved by theta, right, that the center of it would move by theta times r, the radius of the wheel. Okay, we're doing that same thing. The only difference is that x for us is 0 when theta is 10 degrees, right? And so what we need to do is we're not changing by my final theta position. We're changing by the final theta position minus the initial theta position. That's the amount of change that happens, and that should be equal to the amount of distance x traveled that I've got up here.
So you're doing 80 degrees times your
Correct. Yep.
So it's not exactly arc length, or is it exactly arc length?
It is. So I mean, it's angle times radius, which is, you know, I don't have to deal with degrees to radians or any of that because everything internally in Mathcad is radians. Like you can use the degrees as long as you specify its degrees. It'll just immediately turn that into radians as far as how it evaluates anything. All right, so the next part of this is how far does this thing ultimately go before it runs out of steam, right? Before all the energy is spent. And so what we'll do there is we'll do another solve block, okay? What we're trying to find is a new theta. So let me call this one theta max, okay? And I'll just say it, I've got to make an initial guess, so I'll say 1 radian, okay? And again, I always like to change the color on that to make sure I don't forget what I was doing with that particular variable. So here I'll put in given. All right. My basic form of my equation doesn't need to change. Okay, the only thing that needs to change here is what my arguments are. All right, that's the same equation that I used a minute ago, but now what I want to do is everywhere I have a theta f, I want to turn this into a theta max. So that's one of the things I have to do. Oops. That's not a theta. This one's a theta. Okay. Here I need to put in a theta max. And here I need to put in a theta max. Okay, that's one of the things I need to do. What else do you think I need to do to make this proper for the condition that I describe by the furthest that it goes? I'll give you a hint. It has to do with my kinetic energy terms typically. When it goes as far as it's going to go, what are the velocities of things? Zero, right? And the one variable I have in here to describe those velocities is this omega. So I go in and I put omega equals 0 anywhere that I've got an omega. All right. Then I go down here and I'm going to solve for my maximum theta. Okay. And it says that it'll go basically about another 10 degrees or so beyond that 90-degree position that I looked at. All right. If you're curious where all the energy went, right, we can look at all of this stuff up here. All right. All I have to do is I have to put in here the correct value. So I put in a 0, for instance, here, and a max right here. All right. And that'll tell me that's how much change in kinetic energy I had for my half disk. Okay. Does that make sense relative to the last value that I had? It makes sense that it would have lost more kinetic energy, right, than before. Here we can put in 0. Right? So that's how much kinetic energy was lost out of the brake body due to the fact that it decreased the amount of velocity that it had. Okay. Gravitational. Okay, I can put in here theta max. Right? So it lost energy in terms of gravitational potential. Right? Here I can put in theta max. And so the spring, it does make sense that the spring would have gained energy, right, in the process of moving. So that value also makes sense. And then for the work, we put in max like that. And that's how much work was done. You know, by work, it's basically energy transferred into the system, right? We have a negative energy transferred into the system, meaning we lost energy out of the system due to that break. All right. One of the ones I wanted to point out here for gravity, right? See how this number is a little bit less than this number? Does that make sense? Why is that? Yeah, it went back up a little bit. So we were at minimal gravitational energy when we were at 90 degrees, right? And then it began to roll a little bit more, and it started to, achieve some of that gravitational energy back. All right. We can add other things in here if you're curious. What is the force in the spring? I don't know. We can do as many as you want. You can figure out how far did the spring compress, all that good stuff. I won't bore you with all of that, but it's, you know, it's nice because now we've got the crux of the problem solved and you can answer whatever questions you want as far as forces and whatnot. Yes, sir. Yeah. Okay.
Why did we do 15 pounds divided by 30 pounds per inch?
Okay.
Got that 25.
All right. So this expression right here is the one that you're curious about. Let me slide these out of the way. All right. So the formula for the force in a spring is force is equal to spring constant times deflection, right? We were given that the spring had 15 pounds in it before anything moved. Like right at the beginning of the problem, one of the givens was it starts out carrying 15 pounds of compressive force in that spring, right? Well, the only way that spring is carrying 15 pounds of compressive force is if it has the proper amount of deflection to create that force, right? And so I basically just took the F equal K delta equation and flipped it around to give me delta is equal to F over K.
So that's the change in distance.
Right, so well, this is how much the spring is compressed relative to its free length, right? Before anything has happened, right at the beginning of the problem, that's how much it was already compressed. And then it compresses more as x moves according to this other equation, right? So you have the amount that it started out, delta I, and then it adds to that according to those surfaces that compress in on it. Okay. So I'll make one other comment here. This problem would have been a lot easier if those two surfaces had been parallel with one another. Would you agree? Why is that? How much work would it do if work as a function of x if those surfaces were parallel with one another? It's not zero. Let's say you still had that 15 pounds of initial load in the spring. Well, now it wouldn't be variable. It would just move with that 15 pounds. You would take that 15 pounds and multiply it by the coefficient of friction to get your resistive force. And once you know the resistive force, force times length, as long as it's not variable, you just take force times length, and that's work. Okay, so we wouldn't have had to have that integral term. The reason we had to actually integrate there is that this was a function, right? It wasn't just a straight constant. If it's a constant, you don't have to use that integral form of the work expression. Now, I could have made it harder on you as well. I could have gone in here, and instead of these surfaces being flat, right, straight, we could have made those have a shape according to some sort of a function.
Wouldn't you have to actually take into account the top and bottom friction?
You might, yeah. It depends on the reason that his question was, would you have to start, go away from using your small angle approximation and figure out, relatively top and bottom how much is held on each one? And the answer is, if those slopes get large, then this small angle approximation gets less and less valid, right? So yes, you might have to do that. And then if the two slopes were different from one another, right, well then, yeah, you very well might need to do a little system of equations to figure that out. Originally, I had in mind that I might do all of that, and I decided to throw in the small angle approximation and focus on what we're actually doing with this particular section of the course where we're doing this work energy stuff. I could have embroiled us in a pretty long process that isn't necessarily hard, but it's not necessarily what we are trying to learn right now. So I figured I'd focus on what we're trying to learn right now. All right, like it? Questions? All right.